So if you are keeping your photographs on your computer, and if they are precious and don't want to lose them, make sure you back up your valuable stuff on some backup storage. Spare tire, that's an example of using some extra resource to achieve a higher reliability. So even when the fault is there, you can still go on. Now let's look at some terminology. A lot of people, they use these terms interchangeably. Defect, errors, and failures. Now for convenience, in this class, we will kind of use them in this way. So when we will talk about defects, we would mean physical defects. And so like, for example, let's say you have a chip, and the chip has some flaw in it. That's a physical defect. Or software has a coding error in it, so that's a physical defect. Error is the bad information that arises as a result. So a bit gets flipped in a computer, that's an error, or a program is running but value of some variable is incorrect because of some incorrect computation. So we call that error in information. So defects give rise to errors. Now, here is the boundary between internal and external. So this is what we are observing. So as long as the error does not propagate to outside, as long as we don't observe the effect of the error, we say that there has not been a failure. But when the error propagates outside, when we observe the error, we say that the system has had a failure. Now everyone is not this careful, but sometimes we do want to make a distinction, so we will use these terms. Now notice that you can have a latent fault. You can have a fault which has not produced an error, so you have a piece of bad code, but whatever software you are running, that is not using that piece of code, so it has not caused an error. Or a faulty component. So a faulty component will produce an error only when it is used in a process, right? And you can have a latent error. You can have an error in the system, bad data in the system, but if it has not been experienced outside, you will not know. So it's latent. Unfortunately, the terminology is not standard, so you have to watch out for what people actually mean when they use these terms: defects, errors, and failures. Any questions on this? Okay, so we go from 9:30 to 10:45, right? Okay. So, okay, let us see how the defects arise in hardware or software. Now, there are some things for which people are more responsible, and then there are some things that people are not that responsible. I mean, they happen. Good objects wearing out with age. So what can you do? So they naturally age. So if you have a car, that will age with time. And hardware, it ages with time. Incidentally, we will come back to this later on. We will assume later on in our analysis, we will do some quantitative analysis, and we will assume that the hardware is not aging. And you will wonder why, and I will mention the reason, because there are two processes that counteract against each other. But actually, hardware ages. But typically, hardware, like the hardware here on this PC, it ages relatively slowly. It doesn't age that fast. So if I would keep it for maybe, I don't know, 10 years, maybe I might see some signs of aging. Hardware could wear out with age because of incorrect maintenance or operation. Now, it has been pointed out the software can also age. And the reason is, so there's a researcher in software, Barnas. So he came up with a concept of software aging. And this is what he says, that you have the same piece of software, but it runs on a specific operating system. So if you were to run it on a newer operating system, and sometimes it doesn't run. So you can say the software has aged relative to the operating system, because you have a newer operating system and the software is too old. So that is kind of an example of aging. Now some people, they also consider another kind of software aging. Some of the software processes, as they run, they involve some slow degradation, perhaps a gradual memory leak. So you keep on running out of memory or something. And that is also sometimes referred to as software aging. Now, you can have a good object, perfectly good, but it's running in a hostile environment. In that case, we can blame the environment. Your PC is supposed to run within some temperature range. If it is too hot, then your PC may not run quite as well. Now, if you have a marginal object, it may occasionally fail even in environments in which it is supposed to run. So, so these are objects which are kind of tightly designed. They have used some kind of design where they haven't allowed for enough slack. They haven't allowed enough margin. Or maybe the inputs are bad. And then you can have implementation mistakes. So somebody else tells you to write some software, they give you the specifications, but writing the code, you make some mistakes. It is also possible that the specifications they gave you, that could have mistakes. In fact, that's quite common. So defects in hardware or software, they can arise because of many different causes. Now, sometimes we need a fault taxonomy. We need to classify the faults. And so sometimes they will be classified depending on the cause. We just saw it in the previous slide. Sometimes the nature of the fault, whether it's in hardware or software. And if it is in hardware, whether it is a digital fault or it is an analog fault. Analog fault is something that changes an analog attribute. For example, the higher supply current. Sometimes faults are characterized by duration of the fault. A fault can be permanent, and if it is a permanent fault, you basically have to throw away the unit because the fault is permanent and there's nothing you can do about it. On the other hand, the fault could be temporary. Now, intermittent and transient. So you have come across these terms. So do you think they mean the same thing? Intermittent and transient. Sometimes people use them interchangeably. But you could make a distinction. You could use, for marginal systems, you could use the term intermittent, maybe a loose connection. So occasionally when there's some vibrations, there would be some bad operation. Transient, your system is good, but there are some environmental phenomena. So maybe some charged particles that cause soft errors. Now these charged particles that cause soft errors, they're happening all the time. So I have this PC here, and it happens all the time. There's no immunity against charged particles. People have tried to design more robust memories, but now the dimensions are becoming smaller. So transient failures are quite common. So it is possible that sometimes your program may crash for no apparent reason. Just a soft particle hits some memory location and flipped a bit somewhere. Now if you have a permanent fault, but you can fix the fault, and if you can fix it, then you have gone back and basically the fault is gone, so you can classify it under temporary. So this is our fault taxonomy. Any questions on these? Okay, why do we need high reliability? This is kind of a, I guess, maybe 20 years ago, this slide was needed more. Today, people know that you need high reliability, but a while ago, people needed convincing. Okay, you need high reliability for telephone, because telephone switching. Remember, at one time, AT&T, they had a monopoly, and all the telephone network was routed through their telephone switches, and any downtime would cost AT&T a lot of money. So they did actually a lot of studies. Some of the early advances in fault-tolerant computing, they came from AT&T and from telephone switching networks. But now, of course, we take it for granted, right? Transaction processing. So you have banks and airlines, and you must have heard of some problem with the US airline system because some systems were not functioning correctly. So it was something that happened, was that a month, 2 months ago? Some systems were not communicating properly, and that caused delays, and some of the flights couldn't land, and the whole thing was a mess. I think that happened in eastern US. So you need high availability in some systems, and you need high reliability in long life missions where unscheduled maintenance is too costly. For example, the space missions. So you have your spacecraft going to Mars, and it has traveled for maybe a few years or a few months. I forget how long it takes to get there. But any maintenance along the way is, of course, out of the question. In some cases, some manual reconfiguration may be okay. And there are some critical applications where you want them to continue uninterrupted for a long time. And then there are the critical applications. Flight control is one of them. Real-time industrial control. But then a whole lot of applications of fault-tolerant computing happen in ordinary applications, everyday things. So reading music from a CD, you have encoding there to detect any bad bits. Some kind of scheme is already built in, so you would not even notice if it is done properly. But without your error correction scheme in your CDs wouldn't work. Internet packet retransmission, so there's a built-in packet retransmission scheme.